In this video, we'll take a look at two highly popular problems on LeetCode that frequently appear in software engineering interviews. Their main idea is figuring out how to calculate trapped water inside uneven structures, but they differ in one key aspect. The first problem gives you a 1D array of heights, while the second gives you a full 2D matrix. We will walk through their optimal solutions step by step and compare these two problems with each other. Let's first focus on the simpler 1D problem. The core insight is that the water capacity of any single cell depends entirely on the tallest walls to its left and right. Take a look at this cell on the left, for example. Even though there's a tall wall on its right, it can't hold any water because it will just spill out the left side. But if we look at this deep puddle in the middle, it is safely bounded by a maximum height of 2 on the left and 3 on the right. So it perfectly traps 2 units of water. Our challenge is to find these maximums efficiently. To apply this core insight in the most optimal way, we use the 2-pointer technique. We place 1 pointer at the extreme left and 1 at the right. By moving inwards from the edges, we naturally keep track of our maximum walls on both sides. To decide which cell to process, we simply compare our left max and right max. We always process and move the pointer that has the strictly lower maximum, because that side is the absolute bottleneck. By doing this, we guarantee we have enough information to safely trap water using our previous formula. This brilliantly solves the entire problem in a single pass. Let's take a quick look at the Python code for this 2D approach. We set up our left and right pointers and initialize our max_left and max_right variables to keep track of the highest walls we've encountered. Then, we drop into a standard while loop. If the left max is smaller, we know the left side is our absolute bottleneck. So we increment the left pointer and add any trapped water. Otherwise, the right side is the bottleneck, so we decrement the right pointer. Finally, we just return our total trapped water. Boom, done. Let's quickly review the complexity of this optimal 2D approach. We only visit each element exactly once using our 2 pointers. So the time complexity is strictly linear, O of n. And because we only need to keep track of a few variables for pointers and maximums, our space complexity is a perfect O of 1 constant space. As for edge cases, if the array is empty or has less than 3 walls, it physically can't trap any water, so we immediately return 0. Extremely fast, and no extra memory required. Alright, but what happens when we move to 3D? In Trapping Rain Water 2, instead of a flat array, we get an m by n integer matrix. We still need to find the lowest boundary to determine our water level, but we can't do it as simply as the 2-pointer approach. Why? Because in a 3D grid, water doesn't just spill left or right. It can spill out of any of the 4 surrounding sides. A simple left-right approach falls apart instantly. To handle all 4 directions at once, we need a way to constantly track the absolute lowest wall across the entire 3D perimeter. This is where Min-Heap comes into play. Instead of 2 pointers, we take every single cell on the outer border of our grid and throw it into a priority queue. Because water always spills over the lowest possible wall, popping the smallest element from our Min-Heap guarantees we are processing the safest, lowest water level first. Under the hood, a Min-Heap organizes our boundary cells like a tree, where the absolute lowest height naturally bubbles up to the very top. This data structure allows us to efficiently find and extract the smallest wall in logarithmic time, no matter how chaotic the grid gets. So let's run the actual breadth-first search. We pop the lowest block from our heap, and we look at its 4 inner neighbors. If an unvisited neighbor is lower than our current block, congratulations, it traps water. The water fills up exactly to the height of the block we just popped. Once we calculate that trapped water, we push the newly visited neighbor straight into the heap to become part of the new boundary. But wait, there's a massive trick here. When we push that neighbor into the heap, we don't just push its original height. We push the maximum of its original height and the current water level. Why? Think about it. Once a deep valley fills up with water, that standing water essentially solidifies and acts as a brand new, taller virtual wall for the cells next to it. Let's look at the 3D Python implementation. First, we grab the dimensions of the grid and initialize our min-heap and a visited set. We loop through the perimeter, pushing all the border cells into our heap and marking them as visited. Once we heapify that array, we set up our 4 directional offsets for the BFS. Inside the while loop, we pop the lowest cell. For every valid, unvisited neighbor, we check if it's a valley to calculate the trap water, add it to our total, and then push the neighbor into the heap using that critical virtual wall trick. As always, don't forget your edge cases. If the matrix is smaller than 3 by 3, it's mathematically impossible for it to have any inner cells to trap water, so we can just instantly return 0. And of course, making sure you actually add cells to your visited set is crucial so you don't get stuck in an infinite loop. Let's talk about complexity. Since every cell is pushed into the heap exactly once and extracted exactly once, our time complexity is strictly bounded by O of m times n log m times n. As for space complexity, the heap in our visited set will scale linearly with the grid size, giving us O of m times n auxiliary space. It's an incredibly robust and efficient way to process 3D structures. Before we wrap up, let's briefly compare these two problems. In the 2D version, water can only spill left or right. Because our boundary is strictly a 1D line, 2 simple pointers moving inwards are perfectly sufficient to track our maximum bottlenecks. But in 3D, water can spill out in 4 directions anywhere along a complex perimeter. A simple left-right approach collapses here. Instead, we use a min-heap tree to dynamically track and instantly extract the absolute lowest point of our ever-shrinking boundary. Same core logic of finding the minimum bottleneck, but scaled up with a completely different data structure. And that's it. If you enjoyed this visual deep dive into Trapping Rainwater 1 and 2, make sure to like and subscribe for more algorithm masterclasses. Let me know in the comments which problem we should tackle next. See you in the next one.